Hey everybody, Mr. Stone here. Time for some more physics. We're starting our next unit, which is basically on light. We're going to look at the wave nature of light. How is light a wave and how does it behave? We're going to take some of the ideas we learned about waves last year in grade 11 for sound, but we're going to now focus on electromagnetic radiation, which we learned last unit. Follows a couple equations, or four equations, called Maxwell's equations, and it leads us to actually waves, and we'll see how we get there. But before we start, let's start thinking about light. What is light? And we got to go back in time a little bit to history, and when we had two competing ideas. So Newton relied on what he called the corpuscular model. Let me just think. Bodies, things. Light is basically a bunch of little things floating around. So there were some sort of tiny little particles, and they're flying around. Because remember, Newton did all his physics on dynamics. Things traveling around, colliding with each other, accelerating forces, all that sort of stuff. So he tried to apply that to light. So and this led to basically all the stuff that you learned in grade 10 about light and optics, ray optics. One of the big ideas of grade 10 optics is that light travels in straight lines. I think we called it rectilinear propagation. Light, then we drew those ray diagrams or through the lenses and mirrors and all that sort of stuff. And it's a decent model for that. Now, there was another guy around the same time named Christopher Huygens, who was a Dutch physicist, and we talked about his idea, the wave model, using Huygens Principle, and Huygens believed that light was a wave. Okay, now both of these models have certain applications to certain situations, but they also have flaws. So the problem with the corpuscular model, the model of things floating around, light is particles. We can't describe things like diffraction or interference or refraction, things that rely on waves interfering. Okay, can't it has no way of describing that. You fire a whole pile of stuff at an opening, the ones that go through the opening just keep going in straight lines. They don't diffract. Right? But the wave model also doesn't work for some of these newer ideas, things like the photoelectric effect and Compton effect, which we'll talk about in the 5th unit, in our next unit. Okay, so both these models apply to some things, but they both have problems. However, for this unit, we're going to be trying to use the wave model to see if we can understand some phenomena involving light. Okay? And the first thing we're going to look at is basically interference, and how does light interfere with itself. Okay? So before we move on though, let's think about some of the things that we should have learned last year and maybe forgot. But how does a wave itself propagate? How does a wave travel through space? Right? You drop a rock into a pool and a wave goes outwards in a circle. Why? Why does that happen? And one of the ways that we can describe that is something called Huygens Principle, which basically states that if we have a wave front, imagine that this point in the middle here, this is where I dropped a rock, okay? And it's going to spread out, this wave's going to spread out, and it's going to form this red line, which is the wave front. Now we can imagine each dot on here is its own new point source. So that wave itself is going to make a new wave, and each of these are going to make new waves. Now when all those waves add up onto each other, that's going to generate a new wave front. So as each of these wave fronts produce a little circular wave in the direction of propagation, they actually all add up to make a new wave front, and this goes on ad infinitum. In the same way that a straight wave front, like a wave down a beach, let's say, a wave that's coming in towards the beach, each point on here can act like a wave front. Each of these wave fronts are all going to superimpose onto each other to make a new wave front, and the whole thing is going to propagate in the direction that it's moving. Okay, because now I've only drawn 5 here, but really we're talking about an infinite number of these. They're all going to add up, and when they all superimpose onto each other, they're going to make a new wavefront, and that's going to travel. And then that wavefront is itself going to have its own point sources, and we're going to go from there. Okay, so that's how we understand waves to travel. Now this talks about superposition. Hopefully you guys remember superposition. This is when waves, if they stack on top of each other in the same direction, they cause a supercrest, and they cancel out if they go in the opposite direction of each other. Okay, guys remember this? Hope so. All right, so now this leads to the idea of diffraction. So if I have a wave, a straight wave coming across here, and it's going to hit this barrier. So there's this barrier here, you see. Now what's going to happen is we can imagine a whole set, using Huygens Principle, a whole set of these point sources. They're all going to generate their own little waves. And the ones that are together in the middle here are going to generate a sort of a plane wave. And we're going to have sort of plane wave behavior. But on the outsides, we're going to get these curves. And then in the end, we're going to end up with a wavefront that went from being straight to now being curved. Okay? And hopefully you remember these ideas from sound. And sound and waves in grade 11. And this is the reason why you can hear sound through a doorway. You don't have to see the person, but the sound is able to diffract through the doorway, right? So it's quieter, the intensity isn't as loud, but it's still there. The wave is diffracted around there. Okay. Now, does this happen for light? The wavelength of light is very, very small. It's nanometers. It's hundreds of nanometers for visible light, between 400 and 700 nanometers. So if we have a gap that's in that same order, will light diffract? If we get a small enough aperture, does light diffract? And what about two sources? Remember we talked about how two sources can actually interfere with each other and generate constructive interference and destructive interference. Same idea. Remember we walked around the classroom, we moved all the desks, and we walked back and forth, and we heard louder sounds and quieter sounds. Does the same thing happen for light? If we have a gap distance here that's small enough. Now, the first person to show this actually was a guy called Young, and he did a experiment, a very famous experiment, which is we call the Young's double slit experiment. Pardon me. He basically had a lamp here, and he shone it on a single slit. So that now behaved like a diffracting, spreading out wave here. And then he put two slits here. So now these waves, he knows that because he had put one source here, these are now going to come together. They're going to come at the same sort of, the same phase, right? It's going to behave like a point source. A lamp has a filament, especially in this time. This was a long time ago. They didn't have things like lasers. So you take a single slit to produce the light that you want, and then he had that hit these two slits. And he came up with this diffraction pattern, where it's brighter and darker and brighter and darker and so on and so forth, okay? And this happened because these path lengths, if I'm going from, this is more I'm observing at point D, there's a different path length from B to D and from C to D. And they end up causing phase shifts. And if those phase shifts are out of alignment, 180 degrees, it'll be dark. And if the phase shifts aren't, it'll be bright. Okay, just like we saw last year in grade 11. Now, this is much easier to accomplish now because instead of that single slit to begin with, we can just have a laser. A laser produces what we call coherent light. All the light that's coming out of the laser, all the waves are lined up. They're all together. And that just has to do with how the light's produced in the lasing cavity itself. Due to spontaneous emission. A laser is a brilliant idea where you take, well, we'll talk about it let's talk about it in the quantum mechanics unit, okay? A little bit too much right now. But the goal of it, though, is it produces coherent light, so all the light that's coming from it, all the waves are all in phase. Okay? So then if I shine that onto a tiny little grating or a slit here, this is in the order of micrometers, we end up with this pattern. We end up with a diffraction pattern. So this is actual evidence that you can see with your own eyes that light behaves like a wave. It's able to interfere with itself and diffract with itself and produce a wave. Produce a diffraction pattern because the waves are interfering. It's bright where they're constructively interfering and dark where they're destructively interfering. Okay? Now, let's think about the math here for a second. So let's say I have my slit here and I have a screen. Okay? So if I have from the top slit here to the bottom, let's call that a distance of d. Okay. Now there's going to be a path length difference between those two paths. Pardon me. Now, if you look here, so we're having light coming here, they're in phase together, and then if by the time they get to the screen, they're still in phase. Notice they're both going downwards here. Pardon me. They're both going down. So if they're both in phase there, there's going to be a bright spot here. There's going to be constructive interference. So for that to happen, the path difference has to be equal to some multiple of lambda. Okay, so in this case, it's one wavelength. Now it doesn't have to be just one; it can be 2, 3, 4, any multiple of lambda, so that the two waves are in phase. Same thing happens for a dark. It's just that instead of it being a full wavelength, it has to be a half wavelength now. Okay, so now when they're starting out in phase here, so this is down, so they're in phase. Now when they get to here, they're going to be out of phase. One's going to be up and one's going to be down. So they're going to cancel each other out, and it's going to be dark there. So in that case, the path length has to be a half wavelength. And what's this d sine theta? Now that's, if we make this little triangle here, we know that this angle from the perpendicular point here to where I'm measuring here, that's an angle of theta. And using similar triangles, that's going to be this angle here as well. So using trigonometry, if I know that this length here is d, the opposite length here will be equal to d sine theta. So d sine theta represents the path difference, and it has to be equal to lambda for constructive interference, and this path length difference, we can call it delta L is our path length difference. All right, we can call this delta L. And in this case, it's it's delta L. Okay, so that delta L, that change in length that the two light waves have to go, has to be equal to either a full wavelength or a half a wavelength, and multiples of those. This one can be 1, 2, 3, 4. These have to be, now careful here, these have to be odd multiples. So 1, 3, 5, and so on and so forth. Okay. So for us to have a bright fringe, or a bright spot, we have to have some path length difference. Remember, this is the path length difference. Wow, that was not a curly bracket. I'm not sure what that was. Try that again. Better. So that path length difference there has to be equal to some integer multiple of lambda. So then my angle, my sine of my angle, has to be equal to n lambda over d, where d is the space between the two slits. And for a dark fringe, it has to be some half integer of lambda. Okay, so that we can represent by m plus a half, where m is 0, 1, 2, 3, any positive integer. Right, so that makes sense, right? 0 plus a half is a half. So there's our first then 1 plus a half is 3 halves, 2 plus a half is 5 halves, 3 plus a half is 7 halves, and so on and so forth. So for the dark fringe, we can come up with this expression that the sine of the angle has to be equal to m plus a half multiplied by lambda over d. Now, because of these signs, the mathematics can become a little bit complicated, but we have a little cheat. Because we know that, like if you go back to that picture, where is it? Here. You can see here how much the spacing is between them is millimeter range here, right? So this, let's call it delta x, is in the order of millimeters, and this length from here to here is in the order of meters, right? So it's 10 to the 3 difference between the length and x. So that means the angle at which we're talking about are very, very small angles. So if I skip through here, so since I have very, very small angles, this theta here is very small. For small angles, sine theta is the same as tan theta for all intents and purposes. It'll be off on a few, decimals way down the line, but for very small angles that we're dealing with, it's almost equal to tan theta. And tan theta we can deal with more easily because that's going to be opposite over adjacent, or xn, which is going to represent the distance from the center to a bright or a dark fringe, the nth order fringe, whether it's bright or dark. We call it an nth, or we can call it an mth order because we had m for, that's not nice to say mth, but it could be the mth order or the nth order bright or dark fringe. Okay, that's why I have that n. And it's just going to be that xn divided by L, opposite over adjacent, gives us tan theta. So just to prove it to you, the blue line is tan, the red line is sine. If I zoom in anywhere between 5 degrees and -5 degrees, you cannot tell the difference. Things start to diverge here around 10 degrees, -10 degrees, but sine and tan are pretty much the same thing for those small angles, and we're dealing with very small angles, okay, in the orders of less than one degree. So we're talking about this region where they're pretty much the same. So this approximation is very good. So our equations can just simply become the mth order dark fringe if I replace sine theta with approximately tan theta, which is equal to xm over n. The mth order dark fringe is going to be equal to m plus a half lambda L over d. And the bright fringe will just be the integer one. So this one adds an extra half, and this one doesn't. That's the difference. Now this can cause some confusion in terms of what they're telling you, but like, is it the third dark fringe? What number do I mean by that? And you'll see it actually isn't that difficult. You just have to count. Just have to picture in your mind that picture of those fringes and how far have we gone away. And this order number actually is pretty straightforward, but it's an easy place to make a mistake. Instead of putting 3.5, you put 2.5 in the question, and you can get it wrong that way. So just be careful there. All right. So now, what about the spacing between fringes? If I want to know what the spacing between all the fringes, if they're approximately the same, for small angle, they're always going to be the same. For a larger angle, things get a bit weird, but for small angles, the gaps between any of the bright lines or the dark spaces between the bright lines is going to be about the same. So we can look at, and you can see that in the form of our equation here. It's what's it called? Sorry, these are constant, right? The lambda is constant. The length between the slits and the screen is constant, and the slit width, or the spacing between the slits, is constant. So really, it's a linear expression in terms of m. So if I subtract the two, right? If I take the n plus 1, oh sorry, that should be m. That should be an m there. M plus 1, and the m, mth order, that should also be an m, Got mixed up with my n's and m's. Pardon me. If I subtract them, you see the m's are going to cancel. 3/2 minus a half is 2 over 2, which is 1. So really, we end up with this nice little expression that says that the spacing between them is always equal to this constant, lambda L over D. Okay. One thing I'd like you to notice is the longer the wavelength, so the redder the color. Remember here, let's just quickly, 400 nanometers is blue, and 700 nanometers is red, right? So when I talk about redder, we're talking about longer wavelengths. Bluer means shorter wavelengths. So if I increase my wavelength, if I go in the redder direction of the wavelength, the spacing increases. And this is the reason why we have Blu-ray discs, for example. Typically a CD or a DVD player had a red laser because they're cheap and easy to make. And that has a wavelength of 700 nanometers. So you can, really you have you can squeeze more information onto a shorter wavelength laser. Okay, and that has to do with this, and we'll see that later when we talk about diffraction gratings, but not for now. Okay, so let's do some examples here. So let's say we're measuring the wavelength of light from a certain single colored source. Do you direct the light through 2 slits with a separation of 0.15 millimeters? An interference pattern is created on a screen 3 meters away. You find the distance between the first and the 8th consecutive dark lines to be 8 centimeters. What's the wavelength of the source radiating? Now we got to be careful here. So find the distance between the first and the 8th. So what's n in this case? Between 1 and 8. There's 7 spaces between them. So really, we're looking at, and it says that's 8 centimeters. So the space between each one will be 8 divided by 7. Okay. So let's go start with our nice little formula, lambda L over D. That's how we measure that's how we calculate the space between all of them. And rearranging for lambda, we get the space between slits, space between fringes times the spacing divided by L, and replacing everything here. Now be careful here what I did here. I got 0.08 is the spacing between 7. So I divided that by 7 to come up with the spacing between each of them. Multiply that by the space between the slits, divide by the length all the way, and we end up with 570 nanometers. So that's like a greenish, yellowy green. Okay? So that formula is pretty straightforward. Just rearrange it, plug it in, and we're good to go. Okay? Next one. Third order dark fringe of 652 nanometer light is observed at an angle of 15 degrees when the light falls on 2 narrow slits. How far apart are the slits? Okay, so third order dark fringe. Okay, so let's start with the equation for dark fringes. Now I'm using the one that actually has the sign because it gives me the angle, and 15 degrees is quite a large angle, so we can't use the tan. Well, we can, but it's the tan approximation isn't great there. Okay, right, and then I can rearrange that equation for D, which is the space between the slits. And now the question becomes the tricky thing here. I know lambda, I know theta, so I can plug that in. The tricky thing is, what do I plug in there for M? I want the third order dark fringe. Okay, so let's think about that for a second. We're going to have our central point. We're going to have a central maximum here. Right? Let's try that again. Don't like that. We're going to have a central maximum, right? That's going to be our bright spot. It's going to go down to a low spot, and it's going to go up, down, and so forth. Okay, so we're talking about, so there's our first order bright spot, there's our second order bright spot, third order bright spot, fourth order bright spot. Okay, now this is our first dark spot here, this is our second dark spot, and this is our third dark spot. This is where it's dark, okay? So, what number do I really need in the bracket? A half, 1.5, 2.5. So, I need 2.5 or 5 halves. So if you're ever confused, just draw yourself a picture and count from the center here. So this is 1, right? This is 2, and this is 3. Those are the bright spots. So when I want the third order dark spot, that's going to be in between 2 and 3, which is 2.5. So M in this case is 2. Another way you can think about it is if you looked at the definition, M was going from 0, 1, 2, 3, and so forth. So we start at 0. So the third term is 2. Okay, plugging it in, I end up with 630 nanometers, which is, oh, that should be 9. Sorry. No, this is how far apart there. Okay, micrometers. So 6.3 micrometers. All right. So the only tricky thing here, so if you see an angle, use the angle formula. And the only tricky thing is what value of M. Either write out the numbers and figure out which is the third or fifth or whatever they tell you, or draw yourself a picture and use that to figure out what we need there for M. Otherwise, it's pretty straightforward in terms of plugging the numbers. Now, if they'd given you a length away from the screen and a distance, then you'd use the x over L equation. But in this case, since they gave you an angle, we'll just go with the angle equation. All right? So there's a couple, 8 different problems. They're pretty straightforward, same idea. Excuse me. Use these formulas. And we finally have evidence that light is a wave. We still don't know if it's an electromagnetic wave. Spoiler alert, it is electromagnetic wave. You learned that in hopefully grade 10. Right now we now have some evidence and we have some phenomena which we can explain using that idea of light being a wave. Okay, so try these problems. The answers are on the side there, and good luck. All right, so apologize for this lesson being a little bit late. I spent some time putting the whole unit together, and I basically had to rebuild this unit for our distance learning that we're doing here. So I apologize for that, but the next, it's only 6 lessons, and they should follow in pretty quick succession. So best of luck. Hope you guys are staying safe. Miss you all. The weather is beautiful outside, so I hope you guys are out there enjoying the sun. All right. Take care of yourselves.